Hello, this is Mr. Huber. In this lesson, we're going to learn about graphing quadratic equations in the form y equals ax squared plus c. You'll notice there's no bx term in these. We're going to see that another time. For now, graphing y equals ax squared plus c. And those are called quadratic equations when you have the variable squared. Recall, graphing an equation is all the order pairs that are solutions of the equation. And we've seen we can make tables of values, right? We could plug values into the equation, get values out. We did it with linear equations. You can do it with any type of equation. So we can make a table of values to graph a quadratic equation. We're going to start with y equals x squared, which is the parent graph of the quadratic functions. There's nothing in front of the x squared except a 1. There's no b or c value. So we can make a table of values for this so that we'll be able to graph it. So we're going to have x values we'll plug in, y values we'll get out. For the x values, let's just start with 0. If I plugged a 0 in for x, 0 squared would be 0. If I plugged a 1 in for x, 1 squared would be 1. I plug a 2 in for x. 2 squared would be 4 for the y value. Let's try a couple negatives. So negative 1. If I plug in negative 1 and square it, negative 1 times negative 1 is still positive 1. Negative 2 squared would be positive 4. Or if I plugged in, let's say, 3, 3 squared would be 9. And I can get a whole set of tables of values. We're going to see which values are good to plug in for these to get your table, to draw a good graph. For now, we're going to use the values that I made right there. So we're going to have 0, 0 right there. We have 1, 1. We have 2, 4. 3, 9 if I just go down there to keep with my positives. And on the other side of the axis, the y-axis, our other x values that are negative, negative 1, 1, negative 2, 4. And you can probably guess if I plug a negative 3 in, it'd be up here at 9. And a parabola is a curved graph. Do not connect the points with a straight line. You're going to draw a curve through those points. Okay? So it looks kind of like a U shape. Right? Arrows on both ends, it would keep going up forever. Right? So we can plug values in for x. We took these x values, we plugged them into the equation for x, in this case squaring it to get the y value out. And we got some points then that we could graph, and when you draw a parabola, it's going to be a curve, like a U shape. All right, we're going to talk about that here. That's called a parabola. All quadratic equations have a U-shaped graph called a parabola. The lowest or highest point, if it's opening down, we'll see that coming up as well, is called the vertex. So in the problem we just worked on right here, that's the vertex. The vertex is the point 0, 0. So the vertex is a point. It's either the highest or lowest point of the graph. We can see here the lowest point of the graph comes right down here at 0, 0. That's the vertex. The axis of symmetry is the vertical line that goes up and down through the middle of the graph, divides it in half. It goes through the vertex, right through the middle. So this line right here going up and down, right? In this case, that'd be the line x equals 0. That's the axis of symmetry. So the axis of symmetry, it's symmetrical on both sides of that line. It's the same on both sides, cutting it in half. All right. Let's do some more graphing of quadratic equations. So in this instance, we've got y equals 3x squared. We're going to graph it, and we're going to compare it with that parent graph, y equals x squared. So y equals 3x squared. Again, we're going to make a table of values. When you make this table of values, you're going to want to plug in, and I'm going to put them in a little different order than we did last time, negative 2, negative 1, 0, 1, and 2. All right, at least those 5 points. You want to put a couple more to get a more accurate graph? That's good as well. So when I plug a negative 2 into this equation, I plug negative 2 in here. Order of operations, I square that. Negative 2 squared would be 4, times 3 would be 12. So I'd get a 12. When I plug in negative 1, okay, negative 1 squared is 1 times 3 would be 3. 0 squared is 0 times 3 is still 0. When I plug in a 1, I get 1 squared is 1 times 3. Plug in a 2 squared is 4 times 3 is 12. Again, it should be symmetrical. We should see that both points on either side of this vertex, when I plug in negative 1 and when I plug in positive 1, they should come out the same, so that it's symmetrical on both sides. So I'd have the point 0, 0, right there. I have the point 1, 3, and negative 1, 3. And I'd have 2, 12. That'd be up here, kind of off my graph a little bit. Okay? And I have a same shape graph. Okay? Parabola. It's going to be more narrow. Right? It's more narrow. It's kind of stretched out vertically. That's called a vertical stretch, actually. That 3, the a value, is going to affect the graph in how narrow or wide it is. This graph is more narrow. It's called a vertical stretch. So when it says compare to the graph of y equals x squared, it's a vertical stretch by 3. Okay, the factor is 3. So we're multiplying all the y values by 3. If you recall from the parent graph, when I plugged in a 1, I got a 1. Well, this is 1 times 3. When I plugged in a 2, I got a 4. Now it's times 3. It's stretched by a factor of 3. Normally that graph would come out here, right? That y equals x squared graph. Now it's more narrow. All right. Let's look at another example here where we have a y value that's a little different. In this case, negative 1/2 x squared. So negative 1/2 x squared. All right, let's make a table of values. So my table of values, I'm going to plug in those same numbers. Negative 2, negative 1, 0, 1, and 2. When I plug in a negative 2 and square it, negative 2 squared is 4. 4 times a half is 2, and it's a negative there, so it'll be negative 2. So I'm going to have negative 2. When I plug in negative 1 squared is 1 times negative 1/2 would be negative 1/2. Okay. Then when I plug in 0, 0 squared is 0 times anything, it's still going to be 0. I plug in a 1, squared is 1 times negative 1/2. 2 squared is 4 times negative 1/2 is negative 2. So the y values would be negative 2, negative 1/2, 0, negative 1/2, and negative 2. So I can plot those points, 0, 0, 1, and negative 1/2, negative 1 and negative 1/2, 2 and negative 2, and negative 2 and negative 2. So I have my parabola now that would go through those points. And it's going to be wider. That graph is widened out. And it's flipped over. So when your a value is negative, the parabola is going to open down. It's a vertical reflection. Okay? That a value being negative means this is a vertical reflection and shrink by 1/2 or stretch by 1/2. By a factor of 1/2. So it's stretched out, it's wider. Okay? That would be wider. The graph got wider. It's stretched out horizontally, okay, by 1/2. So our parabola is opening down. It would still have a vertex at 0, 0. Right? The axis of symmetry would still be this line here, right? Through the middle, that would be my vertex right there at 0, 0. So pay attention to what happens when this a value is negative. Anytime the a value is negative, your parabola should be opening down. If it's not, then you know there's a mistake. And that negative 1/2 is going to widen the graph out. Before we see some more graphing of parabolas, a little trivia. Triple-double style from the NBA. Who is the first player to average a triple-double for an entire season? Not just doing it in one game or a lot of games, but to have, at the end of the season, average of a triple-double. Means they had 3 different categories where he had more than double digits in those categories. The Big O was his nickname. Oscar Robertson. He played at the University of Cincinnati and then was drafted by Cincinnati in the NBA. And in just his second season in the league, 1961-62, you can see there his statistics. Over 30 points, 12 rebounds, and 11 assists per game, a triple-double for the season. He played for the Milwaukee Bucks for his last 4 seasons of his career after Cincinnati as well, so his 14-year career, pretty good averages there as well. The Big O, Oscar Robertson, the first NBA player to ever average a triple-double over an entire season. All right, let's graph some more parabolas. All right, so now we see the C value is different. So now we have a C value, in this case, of negative 4. So what we're going to want to do here is make a table of values and still plug in negative 2, negative 1, 0, 1, and 2. Negative 2, negative 1, 0, 1, and 2. And when I do this, when I plug in negative 2 in, negative 2 squared is 4, minus 4 is 0. I plug in a negative 1. Squared is 1, minus 4 is negative 3. 0 squared minus 4 would be negative 4. 1 squared, which is 1 minus 4 is negative 3. And 2 squared, 4 minus 4 would be 0. Again, symmetrical. We should get values that are the same on both sides of that middle. Now when I graph this, I'm going to have a point at 0, negative 4. All right? And then from there, I can go either side, negative 1, negative 3, and 1, negative 3. Negative 2, 0, and 2, 0. And when I graph those points, right, I'm going to have my parabola opening up. Should have been a little better there through those points. All right, so we have a parabola opening up through those points, and we can see that it's the parent graph, but it's shifted down. We talk about comparing it. A shift is called a translation. So it's translated down 4 units. Okay, it's translated down 4 units. So the normal parent graph that would be here and opening up. We took the whole thing, we move it all down, and now it's that parabola opening up, but from a vertex now. The vertex isn't at 0, 0. The vertex would be at 0, comma, negative 4. That's the vertex. The axis of symmetry would still be that line through the middle, x equals 0. Right, so that negative 4 is moving the whole graph down by 4. All right, now we got a couple things going on here. Before we even draw the graph, let's talk about what we think might be happening here. So we look at this equation, ax squared plus c. So the a value, the negative 1, that's going to flip the graph over. It should. It's a 1 still, so it's not negative 2 or positive 4 or anything other than 1. So it shouldn't be stretched out either way. It shouldn't be more wide or more narrow than the parent graph. And then the plus 8. Okay, in the last one we had a minus 4 there, and it translated it down 4. So that plus 8, you might guess, is going to move the whole graph up 8. So let's make a table of values, and we'll see what that looks like. So I make my table of values. I'm going to plug in negative 2, negative 1, 0, 1, and 2. Plug in a negative 2. Now when I plug negative 2 in here, squared is 4, but it's negative now. So 4 with a negative. So negative 4 plus 8, which is 4. And then I have negative 1. When I plug a negative 1 into there, I get 1. And it's a negative 1 plus 8 would be 7. And now when I plug in a 0, 0 squared is 0. Negative 0 is still just 0, plus 8 would be 8. When I plug in a 1, I get negative 1 plus 8 is 7. 2 squared is 4. Negative 4 plus 8 would be 4. So I plug those values in. I got my y values. And now I can, looks like an x again, that's a y. So now I can plot these points. So I have negative 2, comma 4, negative 1, comma 7, 0, comma 8, 1, comma 7, and 2, comma 4. And I can draw my parabola through those points. Okay? And I've got my opening down, as we expected. Right? That negative value means it's opening down, the plus 8. So instead of the vertex being here, the whole thing was shifted up 8. And it would normally open up from there. By shifting up 8, the negative for the a value is now going to open it down. So it's a reflection across the x-axis. That's also called a vertical reflection. So vertical reflection across the x-axis is flipped down over the x-axis, and it's translated up 8, right? So it's translated up 8. So that's the comparison part. That's how it could compare to the normal parent graph of just y equals x squared. Now let's look at what those look like together on the same graph. Just kind of recap everything we've seen here from what happens with these a and c values. All right, we can see here in this first example, right, just a is greater than 0. So when the a is greater than 0, it's going to open up because it's a positive a value. If the a is bigger than 1, right, this blue graph would just be the y equals x squared. When it's more narrow, like when we saw ours where this was another number, other than, like, say it's 3 or 5 or something for the a value, that narrows it down, narrows the parabola, right? It stretches it vertically. It widens out when the a value is between 0 and 1. So if it's like 1/2, like we saw in one of ours, okay, it's wider than the blue parent graph. Or here the blue parent graph, when the negative a value, when a is less than 0. Negative a values can open down, still more narrow when the a value is bigger, and when it's between 0 and negative 1, widens out. And then the c value, so the a value affects how wide or narrow it is and whether it's opening up or down, and the c value affects where it moves up or down. Okay? Not flipped over up or down, okay, but just moving the graph up or down. Okay? So we can see that when we have the c value of 0 and there's no c value, that's our parent graph. When it was plus something, like whenever we moved it up, if it was minus something, we move it down. So we can see what happens here in the terms: vertical stretches, okay, reflections, okay, translation, okay, shifting the graph. So know those mathematical terms as well, so you're familiar with them and you know what they mean when we see them in terms of these graphs. A parabola is a U-shaped graph for any quadratic equation. Remember, the vertex is the highest or lowest point, so the vertex would be this highest or lowest point, okay, on the parabola, and know how the a and the c value affect what that graph will look like.